Chapter 17, Object-Oriented Programming Features of Rust. Object-Oriented Programming, OOP, is a way of modeling programs. Objects came from Samala in the 1960s. Those objects influenced Alan Kay's programming architecture in which objects pass messages to each other. He coined the term object-oriented programming in 1967 to describe this architecture. Many competing definitions describe what OOP is. Some definitions would classify Rust as an object-oriented, but other definitions would not. In this chapter, we'll explore certain characteristics that are commonly considered object-oriented and how those characteristics translate into idiomatic Rust. We'll then show you how to implement an object-oriented design pattern in Rust and discuss the trade-offs of doing so versus implementing a solution using some Rust strengths instead. Characteristics of object-oriented languages. There is no consensus in the programming community about what features a language must have to be considered object-oriented. Rust is influenced by many programming paradigms, including OOP, for example. We explored the features that come from functional programming in Chapter 13. Arguably, OOP languages share certain common characteristics, namely objects, encapsulation, and inheritance. Let's look at what each of those characteristics means and whether Rust supports it. Objects contain data and behavior. The book Design Patterns, Elements of Reusable Object-Oriented Software by Erich Gamma, Richard Helm, Ralph Johnson, and John Velicides, Addison Wesley Professional 1994, colloquially referred to as the Gang of Four book, is a catalog of object-oriented design patterns. It defines OOP this way. Object-oriented programs are made up of objects. An object packages both data and procedures that operate on data. The procedures are typically called methods or operations. Using this definition, Rust is object-oriented. Structs and enums have data, and impl blocks provide methods on structs and enumerations. Even though structs and enumerations are methods, with methods aren't called objects, they provide the same functionality according to the Gang of Four's definition of objects. Encapsulation that hides implementation details. Another aspect commonly associated with OOP is the idea of encapsulation, which means that the implementation details of an object aren't accessible to code using that object. Therefore, the only way to interact with an object is through its public API code. Using the object shouldn't be able to reach into the object's internals and change data or behavior directly. This enables the programmer to change and refactor an object's internals without needing to change the code that uses the object. We discussed how to control encapsulation in Chapter 7. We can use the pub keyword to decide which modules, types, functions, and methods in our code should be public, and by default everything else is private. For example, we can define a struct average collection that has a field containing a vector of I32 values. The struct can also have a field that contains the average of values in a vector, meaning the average doesn't have to be computed on demand whenever anyone needs it. In other words, average collection will cache the calculated average for us. Listing 17-1 has the definition of the average collection struct. Listing 17-1, an average collection struct that maintains a list of integers and the average of the items in the collection. The struct is marked public so that the other code can use it, but the fields within the struct remain private. This is important in this case because we want to ensure that whenever a value is added or removed from the list, the average is also updated. We do this by implementing add, remove, and average methods on the struct as shown in listing 17-2. Listing 17-2 implementations of the public methods add, remove, and average on averaged collection. The public methods add, remove, and average are the only ways to access or modify an instance of averaged collection. When an item is added to the list using the add method or removed using the remove method, the implementation of each call is private update_average method that handles updating the average field as well. We leave the list and average fields private so that there's no way for external code to add or remove items to the list field directly. Otherwise, the average field might become out of sync when the list changes. The average method returns the value in the average field, allowing external code to read the average but not modify it. Because we've encapsulated the implementation details of the struct average collection, we can easily change aspects such as the data structure in the future. For instance, we could use a hash set I32 instead of a vector vec I32 for the list field, as long as the signature of the add, remove, and average public method stays the same. Code using the average collection wouldn't need to change. If we made list public instead, this wouldn't necessarily be the case. Hash set I32 and vec I32 have public methods for adding and removing items, so the external code would likely have to change if it were modifying lists directly. If encapsulation is a required aspect for a language to be considered object-oriented, then Rust meets that requirement. The option to use public or not for different parts of the code enables encapsulation of implementation details. Inheritance as a type system and as code sharing. Inheritance is a mechanism whereby an object can inherit from another object's definition, thus gaining the parent's object data and behavior without you having to define them again. If a language must have inheritance to be an object-oriented language, then Rust is not one. There is no way to define a struct that inherits the parent struct's field and method implementations. However, if you're used to having inheritance in your programming toolbox, you can use other solutions in Rust, depending on your reason for reaching for inheritance in the first place. If you choose inheritance for two main reasons, one is for reuse of code, you can implement particular behavior for one type. And inheritance enables you to reuse that implementation for a different type. You can share Rust code using different trait method implementations instead, which you saw in listing 10-14, when we added a default implementation of the summarize method on the summary trait. Any type implementing the summary trait would have the summarize method available on it without any further code. This is similar to a parent class having an implementation of a method and an inheriting child class also having the implementation of method. We can also override the default implementation of the summarize method when we implement the summary trait, which is similar to a child class overriding the implementation of a method inherited from a parent class. The other reason to use inheritance relates to the type system, to enable a child type to be used in the same places as the parent type. This is also called polymorphism, which means you can substitute multiple objects for each other at runtime if they share certain characteristics. Polymorphism. To many people, polymorphism is synonymous with inheritance, but it's actually a more general concept that refers to code that can work with data of multiple types. For inheritance, those types are generally subclasses. Rust instead uses generics to abstract over different possible types and trait bounds to impose constraints on what those types must provide. This is sometimes called bounded parametric polymorphism. Inheritance has recently fallen out of favor as a programming design solution in many programming languages because it's often a risk of sharing more code than necessary. Subclasses shouldn't always share all characteristics of their parent class, but will do so with inheritance. This can make a program's design less flexible. It also introduces the possibility of calling methods on subclasses that don't make sense or that could cause errors because the methods don't apply to the subclasses. In addition, some languages will only allow subclasses to inherit from one class, further restricting the flexibility of a program's design. For that reason, Rust takes a different approach, using a trait objects instead of inheritance. Let's look at how trait objects enable polymorphism in Rust. Using trait objects that allow for values of different types. In Chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing 8-10 where we defined a spreadsheet cell enumeration that had variants to hold integers, floats, and text. This meant we could store different types of data in each cell and still have a vector that represented a row of cells. This is a perfectly good situation when our interchangeable items are a fixed set of types that we know when our code is compiled. However, sometimes we want our library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example graphical user interface GUI tool that iterates through a list of items, calling a draw method on each one to draw it to the screen. A common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image, and another might add a select box. We won't implement a fully fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing the library, we can't know and define all types other programmers might want to create. But we do know that GUI needs to keep track of many values of different types, and it needs to call a draw method on each of these differently typed values. It doesn't need to know exactly what will happen when we call the draw method, just that the value will have the method available for us to call. To do this in a language with inheritance, we might define a class named component that has a method named draw on it. The other classes, such as button, image, and select box, would inherit from component and thus inherit the draw method. They could each override the draw method to define their custom behavior, but the framework could treat all of the types as if they were component instances and call draw on them. But because Rust doesn't have any inheritance, we need another way to structure the GUI library to allow users to extend it with new types. Defining a trait for common behavior. To implement the behavior we want GUI to have, we'll define a trait named draw that will have one method named draw. When we can define a vector, then we can define a vector that takes a trait object. A trait object points to both an instance of a type implementing our special trait as well as a table used to look up trait methods on the type at runtime. We create a trait object by specifying some sort of pointer, such as methods on that type at runtime. I'm reading the same line over and over again. We create a trait object by specifying some sort of pointer, such as a reference or a box T smart pointer, then the dynamic keyword, and then specifying a relevant trait. We'll talk about the reason traits objects must use a pointer in Chapter 19 in the section Dynamically Sized Types and the Sized Trait. We can use the trait object in place of a generic or concrete type. Wherever we use a trait object, Rust's type system will ensure at compile time that any value used in that context will implement the trait object's trait. Consequently, we don't need to know all of the possible types at compile time. We've mentioned that in Rust we refrain from calling structs enumerations objects to distinguish them from other languages' objects. In a struct or enumeration, the data in the struct field and the behavior in the implement blocks are separated, whereas in other languages the data and the behavior combined into one concept is often labeled as an object. However, trait objects are more like objects in other languages in the same sense that they combine data and behavior. But trait objects differ from traditional objects in that we can add the data to trait object. Trait objects aren't as generally useful as objects in other languages. Their specific purpose is to allow abstraction across common behavior. Listing 17-3 shows how to define a trait named draw with one method named draw. Listing 17-3 definition of the draw trait. This syntax should look familiar from our discussions on how to define traits in Chapter 10. Next comes new syntax. Some new context. Listing 17-4 defines a struct named screen that holds a vector named components. This vector is of type box dynamic draw, which is a trait object. It's a stand-in for any type inside a box that implements a draw trait. Listing 17-4 definition of the screen struct with a component field holding a vector of trait object that implement the draw trait. On the screen struct, we'll define a method named run that will call the draw method on each of its components, as shown in listing 17-5. Listing 17-5, a run method on screen that calls the draw method on each component. This works differently from defining a struct that uses a generic type parameter with trait bounds. A generic type parameter can only be substituted with one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the trait object at runtime. For example, we could have defined the screen struct using a generic type and a trait bound as in listing 17-6. Listing 17-6, an alternate implementation of the screen struct and its run method using generics and trait bounds. This restricts us to a screen instance that has a list of components, all of the type button, or all of type text field. If you'll only ever have homogeneous collections, using generics and trait bounds is preferable because the definitions will be morphometamorphized at compile time to use the concrete types. On the other hand, with the method using trait objects, one screen instance can hold a vector t that contains a box button, as well as a box text field. Let's look at how this works, and then we'll talk about the runtime performance implications. Implementing the trait. Now we'll add some type to the implement to it. Now we'll add some types that implement the draw trait. We'll provide the button type. Again, actually implementing the GUI library is beyond the scope of this book, so the draw method won't have any useful implementation in its body. To imagine what the implementation might look like, a button struct might have fields for width, height, and label, as shown in listing 17-7. Listing 17-7, a button struct that implements the draw trait. The width, height, and label fields on button will differ from the fields on other components such as text field type that might have those fields plus a placeholder field instead. Each of the types we want to draw on the screen will implement the draw trait, but it will use different code in draw method to define how to draw that particular type, as button has here without the actual GUI code. which is beyond the scope of this chapter. The button type, for instance, might have an additional implementation block containing methods related to what happens when a user clicks the button. These kind of methods won't apply to types like text field. If someone using our library decides to implement a select box struct that has width, height, and option fields, they implement the draw trait on the select box type as well, as shown in listing 17-8. Listing 17-8, another crate using GUI and implementing the draw trait on a select box struct. Our library's user can now write their main function to create a screen instance. To the screen instance, they can add a select box and a button by putting each in a box T. To become a trait object, they can then call the run method on the screen instance, which will call draw on each of the components. Listing 17-9 shows this implementation. Listing 17-9 using trait objects to share values of different types that implement the same trait. When we wrote the library, we didn't know that someone might add the select box type, but our screen implementation was able to operate on the new type and draw it because select box implements the draw trait, which means it implements the draw method. This concept of being concerned only with the message a value responds to rather than the value's concrete type is similar to the concept of duck typing in dynamically typed languages. If it walks like a duck and it quacks like a duck, then it must be a duck. In the implementation of run on screen in listing 17-5. Run doesn't need to know that the concrete type of each component, what the concrete type of each component is. It doesn't check whether a component is an instance of a button or a select box. It just calls the draw method on the component. By specifying box dynamic draw as the type of the values in the component's vector, we've defined screen to need values that we can call the draw method on. The advantage of using trait objects and Rust type system to write code similar to code using duck typing is that we never have to check whether a value implements a particular method at runtime or worry about getting errors. If a value doesn't implement a method, but we call it anyway, Rust won't compile our code if the value doesn't implement the trait that the trait object needs. For example, listing 17-10 shows what happens if we try to create a screen with a string as a component. Listing 17-10, attempting to use a type that doesn't implement the trait object's trait. We'll get this error because string doesn't implement the draw trait. This error lets us know that either we're passing something to screen we didn't mean to pass and we should pass a different type, or we should implement draw on string so that the screen is able to call draw on it. Trait objects before dynamic dispatch. Recalling the performance of code using generics section in chapter 10, Our discussion on the morphosization process performed by the compiler when we use the trait bounds on generics. The compiler generates non-generic implementations of functions and methods for each concrete type that we use in place of generic type parameter of a generic type parameter. The code that results from morphosization is doing static dispatch. This is when the compiler knows what method you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time what method you're calling in. Dynamic dispatch cases, the compiler emits code that at runtime will figure out which method to call. When we use trait objects, Rust must use dynamic dispatch. The compiler doesn't know all of the types that might be used with the code that is using trait objects, so it doesn't know which method implementation on which type to call. Instead, at runtime, Rust uses the pointers inside the traits object to know which method to call. There is a runtime cost when this lookup happens that doesn't occur with static dispatch. Dynamic dispatch also prevents the compiler from choosing to inline a method's code which in turn prevents some optimizations. However, we did get extra flexibility in the code that we wrote in listing 17-5 and we're able to support in the listing 17-9, so it's a trade-off to consider. Online safety is required for trait objects. You can only make object-safe traits into trait objects. Some complex rules govern all the properties that make a trait object safe. But in practice, only two rules are relevant. A trait object is safe if all of the methods defined in the trait have the following properties. The return type isn't self, and there are no generic type parameters. The self keyword is an alias for the type we're implementing the trait or methods on. Trait objects must be object safe because once you've used a trait object, Rust no longer knows the concrete type that's implementing that trait. If a trait method returns the concrete self type, but the type object forgets the exact type of self is, there's no way the method can use the original concrete type. The same is true of generic type parameters that are filled in with concrete type parameters when the trait is used. The concrete types become the part of the type that implements the trait. When the type is forgotten through the use of trait object, there is no way to know what types to fill in the generic type parameters with. An example of a trait whose methods are not object safe is the standard library's clone trait. The signature for the clone method in the clone trait looks like this. The string type implements the clone trait, and when we call the clone method on the instance of string, we get back an instance of string. Similarly, if we call clone on an existence of vector t, we get back an instance of vector t. The signature of clone needs to know that what type will stand in for self because that's the return type. The compiler will indicate when you're trying to do something that violates the rules of object safety in regards to trait objects. For example, let's say we tried to implement the screen struct in listing 17-4 to hold types that implement the clone trait instead of the draw trait like this. We would get this error. This error means you can't use this trait as a trait or object in this way. If you're interested in more details on object safety, see Rust RFC 255. Implementing an object-oriented design pattern. The state pattern is an object-oriented design pattern. The crux of the program is that a value has some internal state, which is represented by a set of state objects, and the value's behavior changes based on the internal state. The state's objects share functionality. In Rust, of course, we use structs and traits rather than objects and inheritance. Each state's state object is responsible for its own behavior and for governing when it should change into another state. The value that holds the state object knows nothing about the different behavior of the states or when the transition between states, or when to transition between states. Using the state pattern means when the business requirements of the program change, we won't need to change the code of the value holding the state or the code that uses the value. We only need to update the code inside one of the state's objects to change the rules or perhaps add more state objects. Let's look at an example of the state design pattern and how to use it in Rust. We'll implement a blog post workflow in an incremental way. The blog's final functionality will look like this. 1. A blog post starts as an empty draft. 2. When the draft is done, a review of the post is requested. 3. When the post is approved, it gets published. And 4. Only published blog posts return content to print, so unapproved posts can't accidentally be published. Any other changes attempted on a post should have no effect. For example, if we try to approve a draft blog post before we've requested a new review, that post should remain an unpublished draft. Enlisting 17-11 shows this workflow in code form. This is an example usage of the API will implement in a library crate named blog. This won't compile yet because we haven't implemented the blog crate yet. Listing 17-11, code that demonstrates the desired behavior we want our blog crate to have. We want to allow the user to create a new draft blog post with post : new. Then we want to allow text to be added to the blog post while it's in the draft state. If we try to get the post's content immediately before approval, nothing should happen because the post is still a draft. We've added assert underscore EQ exclamation mark in the code for demonstration purposes. An excellent unit test for this would be to assert that a draft blog post returns an empty string from the content method, but we're not going to write tests for this example. Next, we want to enable a request for a review of the post, and we want content to return an empty string while waiting for the review. When the post receives approval, it should get published, meaning the text of the post will be returned when content is called. Notice that the only type we're interacting with from the crate is the post type. This type will use the state pattern and will hold a value that will be one of the three state objects, representing the various states a post can be in: draft, waiting for review, or published. Changing from one state to another will be managed internally within the post type. The states change in response to methods called by our library's users on the post instance, but they don't have to manage the state's changes directly, so also users can't make a mistake with the states, like publishing a post before it's reviewed. Defining post and create a new instance in the draft state. So let's get started on the implementation of the library. We know we need a public post struct that holds some content, so we'll start with the definition of the struct and an associated public new function to create an instance of post, as shown in listing 17-2. We'll also make private state traits. Then post will hold a trait object of box dynamic state inside an option T in a private field named state. You'll see why the option T is necessary in a bit. Listing 17-12, definition of a post struct and a new function that creates a new post instance, a state trait, and a draft struct. The state trait defines the behavior shared by different post states, and the draft pending review and published states will all implement the state trait. For now, the trait doesn't have any methods, and we'll start by defining just the draft state because that is the state we want in a post to start in. When we create a new post, we set its state field to a sum value that holds a box. This box points to a new instance of the draft struct. This ensures whenever we create a new instance of posts, it will start out as a draft because the state field of post is private. There is no way to create a post in any other state. In the post : new function, we set the content fields to a new empty string, storing the text of the post content. Listing 17-11 showed that we want to be able to call a method named add_user and pass it a reference string that is added to the text content of the blog post. We implement this as a method rather than exposing the content field as public. This means we can implement a method later that will control how the content field's data is read. The add_text method is pretty straightforward, so let's add an implementation in listing 17-13 to the implementation post block. Listing 17-13, implementing the address_text method to add text to a post content. The add underscore text method takes a mutable reference to self because we're changing the post instance that we're calling add underscore text on. Then we call publish underscore string on the string in content and pass the text argument to add to the saved content. This behavior doesn't depend on the state of the post is in. It's not part of the state pattern. The add underscore text method doesn't interact with the state field at all, but it is part of the behavior we want to support. Ensuring the content of a draft post is empty. Even after we've called add underscore text and added some content to our post, we still want the content method to return an empty string slice because the post is still in the draft state as shown on line 7 of listing 17-11. For now, let's implement the content method with the simplest thing that will fulfill the ability to change a post state so it can be published. So far, posts can only be in the draft state, so the post content should always be empty. Listing 17-14 shows the placeholder implementation. Listing 17-14, adding a placeholder implementation for the content method on post that always returns an empty string slice. With this added content method, everything in listing 17-11 and up to line 7 works as intended. Requesting a review of the post changes its state. Next, we need to add functionality to the request to request a review of post. This should change the state from draft to pending review. Listing 17-15 shows this code. Listing 17-15, implementing request underscore review methods on post and the state trait. We give post a public method name, request underscore review, that will make a mutable reference to self when we call an internal request underscore review method on the current state of post. And the second request underscore review method consumes the current state and returns a new state. We've added the request underscore review method to the state trait. All types that implement the trait will now need to implement the request underscore review method. Note that rather than having self, reference self, or reference mute self as the first parameter of the method, we have self colon box self. This syntax means the method is only valid when called on a box holding the type. This syntax takes ownership of the box self, invalidating the old state so the state value of the post can transform into a new state. To consume the old state, the request underscore review method needs to take ownership of the state value. This is where the option in the state field of post come in. We call the take method to take the sum value out of state field and leave a none in its place because Rust doesn't let us have unpopulated fields in structs. This lets us move the state value out of post rather than borrowing it. Then we'll set the post state value to the result of the operation. We need to set state to none temporarily rather than setting it directly with code like self.state equals self.state.request underscore review and parentheses semicolon to get ownership of the state value. This ensures post can't use the old state value after we've transformed it into the new state. The request underscore review method on draft needs to return a new boxed instance of a new pending review struct, which represents the state when a post is waiting for review. The pending review struct also implements the request underscore review method, but doesn't do any transformations. Rather, it returns itself because when we request a review on a post already in the pending review state, it should stay in the pending review state. Now we can start seeing the advantages of the state pattern. The request underscore review method on post is the same no matter its state value. Each state is responsible for its own rules. We'll leave the content method on post as is, returning an empty string slice. We can now have post in the pending review state as well as in the draft state, but we want the same behavior the pending review state. Listing 17-11 now works up to line 10. Adding the approved method that changes the behavior of content. The approved method will be similar to the request underscore review method. It will set state to the value that the current state says it should have when the state is approved, as showing in listing 17-16. Listing 17-16, implementing the approved method on post and the state trait. We added the approved method to the state trait and add a new struct that implements state, the published state. Similar to request underscore review, if we call the approved method on a draft, it will have no effect because it will not return self. When we call approve on pending review, it returned a new boxed instance of the published struct. The published struct implements the state trait, and for both the request underscore review method and the approved method, it returns itself because the post should stay in the published state in those cases. Now we need to update the content method on post. If the state is public, we want to return the value in the post contents field. Otherwise, we want to return an empty string slice as shown in listing 17-17. Listing 17-17, updating the content on method on post to delegate to content method on state. Because the goal is to keep all these rules inside the structs that implement state, we call a content method on a value in state and pass the post instant that is self as an argument. Then we return a value that is returned from using the content method on the state value. We call the as underscore reference method on the option because we want a reference to the value inside the option rather than ownership of the value. Because state is an option box dynamic state, when we call as underscore reference, an option reference box dynamic state is returned. If we didn't call as underscore reference, we would get an error because we can't move state out of the borrowed reference self and the function parameter. We then call the unwrap method, which we know will never panic because we know the method on post ensures that state will always contain some value when those methods are done. This is one of the cases we talked about in the cases in which you have more information than the compiler section of chapter 9. When we know that a none value is never possible even though the compiler isn't able to understand that. At this point, when we call content on the reference box dynamic state deference dereference deref coercion will take effect on reference and the box, so the content method will ultimately be called on the type and implements the state trait. That means we need to add content to the state trait definition, and that is where we'll put up the logic for what content to return depending on which state we have, as shown in listing 17-18. Listing 17-18, adding the content method to the state trait. We added the default implementation for the content method that returns an empty string slice. That means we don't need to implement content on the draft and pending review structs. The publish struct will override the content method and return the value in post.content. Note that we need lifetime annotations on this method. As we discussed in chapter 10, we're taking a reference to a post as an argument and returning a reference to part of that post. So the lifetime of the returned reference is related to the lifetime of the post argument. And we're done. All of the listing 17-11 now works. We've implemented the state pattern with the rules of the blog post workflow. The logic related to the rules lives in the state objects rather than being scattered throughout post. Trade-offs of the state pattern. We've shown that Rust is capable of implementing the object-oriented state pattern to encapsulate the different kinds of behavior a post should have in each state. The methods on post know nothing about the various behaviors. The way we organize the code, we have to look in only one place to know the different ways a published post can behave. The implementation of the state of trait on the published struct. If we were to create an alternative implementation that didn't use the state pattern, we might instead use match expressions in the methods on post, or even in the main code that checks the state of the post and changes behavior in those places. That would mean we would have to look in several places to understand all of the implications of a post being in the published state. This would only increase the more states we add. Each of those match expressions would need another arm. With the state pattern, the post method, and the places we use post don't need match expressions. And to add a new state, we would only need to add a new struct and implement the trait methods on that one struct. The implementation using the state pattern is easy to extend to add more functionality. To see simplicity of maintaining code that offers the state pattern, try a few of these suggestions. Add a reject method that changes the post state from pending review back to draft. Require 2 calls to approve before the state can be changed to published, and allow users to add text content only when a post is in the draft state. Hint, have the state object responsible for what might change about the content, but not responsible for modifying the post. One downside of the state pattern is that because the state implement the transitions between states, some of the states are coupled to each other. If we add another state between pending review and published, such as scheduled, we would have to change the code in pending review to transition to schedule instead. It would be less work if pending review didn't need to change with the addition of a new state, but that would mean switching to another design pattern. Another downside is that we've duplicated some logic. To eliminate some of the duplication, we might try to make default implementations for the request underscore review and approve methods on the state, trait, and return self. However, this would violate object safety because the trait doesn't know what the concrete self will be exactly. We want to be able to use the state as a trait object, so we need its methods to be object safe. Other duplication includes the similar implementations of the request underscore review and the approve methods on post. Both methods delegate to the implementation of the self method on the value in the states field of option and set the new value of the state field to the result. If we had a lot of methods on post that followed this pattern, we might consider defining a macro to eliminate the repetition. See the macros section in Chapter 19. By implementing the state pattern exactly as it's defined for object-oriented languages, we're not only taking advantage of Rust's strengths as we could. Let's look at some changes that could make that some changes we can make to the blog crate that can make invalid states and transitions into compile time errors. Encoding states and behavior as types. We'll show you how to rethink the state pattern to get different set of trade-offs. Rather than encapsulating the states and transitions completely so outside code has no knowledge of them. We'll encode some states into different types. Consequently, Rust type checking system will prevent attempts to use draft posts where published posts are allowed by issuing a compiler error. Let's consider the first part of main in listing 17-11. We still enabled the creation of new posts in the draft state using position : new and the ability to add text to the post content, but instead of having a content method on a draft post that returns an empty string, we'll make it so draft posts don't have the content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us the method doesn't exist. As a result, it will be impossible for us to accidentally display draft post content in production because the code won't even compile. Listing 17-19 shows the definition of a post in post struct and a draft post struct, as well as methods on each. Listing 17-19, a post with a content method and a draft post without a content method. Both the post and draft post structs have a private content field that stores the blog post text. The structs no longer have the state field because we're moving the encoding of the state to types of the structs. The post struct will represent a published post, and it has a content method that returns the content. We still have a post colon or post. Let's see, what is that again? Colon post colon. We still have a post new function, but instead of returning an instance of post, it returns an instance of draft post. Because content is private and there aren't any functions that return post, it's not impossible to create an instance of post right now. It's not possible to create an instance of post right now. The draft post struct has an add underscore text method, so we can add text to content as before. But note that draft post does not have a content method defined. So now the program ensures all posts start as draft posts, and draft posts don't have their content available for display. Any attempt to get around these constraints will result in a compiler error. Implementing transitions as transformations into different types. So how do we get a published post? We want to enforce the rule that a draft post has to be reviewed and approved before it can be published. A post in the pending review state should still not display any content. Let's implement these constraints by adding another struct, pending review post, defining the request underscore review method on draft post to return a pending review post, and defining an improved method on pending review post to return a post as shown in listing 17-20. Listing 17-20, a pending review post that gets created by calling request underscore review on draft post, and an improved method that turns a pending review post into a published post. The request underscore review and approved methods take ownership of self, thus consuming the draft post and pending review post instances and transforming them into pending review post and a published post, respectively. This way we don't have any lingering draft post instances after we call request underscore review on them, and so forth. The pending review post struct doesn't have a content method defined on it, so attempting to read its content results in a compiler error. as with draft post, because the only way to get a publish post instance is that does have a content method defined is to call the approved method on a pending review post. And the only way to get a pending review post is to call the request underscore review method on a draft post. We've now encoded the blog post workflow into the type system. But we also have to make small changes to main, the request underscore review, and approved method return new instances rather than modifying the struct they're calling on. So we need to add more let post equal shadowing assignments to save the returned instances. We also can't have the assertions about the draft and pending review post contents be empty strings, nor do we need them. We can't compile code that tries to use the content of posts in those states any longer. The updated code in main is shown in listing 17-21. Listing 17-21, modifications to main to use the new implementation of the blog post workflow. The changes we needed to make to the main to reassign post mean that this implementation does not quite follow the object-oriented state pattern anymore. The transformations between the states are no longer encapsulated entirely within the post implementation. However, our gain is that valid states are now possible because of the type system and the type checking that happens at compile time. This ensures that certain bugs such as display of the content of an unpublished post will be discovered before they make it to production. Try the tasks suggested for additional requirements that we mentioned at the start of the section on the blog. Create as it is after listing 17-20 to see what you think about the design of this version of the code. Note that some of the tasks might be completed already in this design. We've seen that even though Rust is capable of implementing object-oriented design patterns, other patterns such as encoding states into the type system are also available in Rust. These patterns have different trade-offs. Although you might be familiar with object-oriented patterns, rethinking the problem to take advantage of Rust features can provide benefits, such as preventing some bugs at compile time. Object-oriented patterns won't always be the best solution in Rust due to certain features, like ownership, that object-oriented languages don't have. Summary: no matter whether or not you think Rust is an object-oriented language after reading this chapter, you don't know that you can use trait objects to get some object-oriented features in Rust. See, you now know that you can use trait objects to get some object-oriented features in Rust. Dynamic dispatch can give your code some flexibility in exchange for a bit of runtime performance. You can use this flexibility to implement object-oriented patterns that can help your code's maintainability. Rust also has other features like ownership that object-oriented languages don't have. An object-oriented pattern won't always be the best way to take advantage of Rust's strengths, but it is an available option. Next, we'll look at patterns, which are another of Rust's features that enable lots of flexibility. We've looked at them briefly throughout the book, but haven't seen their full capability yet. Let's go. Okay, so that concludes chapter 17. Next is chapter 18.